Hey, good morning. All right, Ellie's here. Oscar's here. Bella's here. Lola's here. Lycia's here. Antonin's here. Chelsea's here. Good morning. Penelope's here. Louise is here. Great. Thank you for joining me. Let's see if some others showed up. We've got 9 of you. That's cool. While we're waiting for others, you can look at the board. I've graded about half of the 6 solutions lab that has been sitting around for a while. I'm finally getting to it. And we got some problems, and it's an AP basic. You need to know how to write net ionic reactions. Okay? So find the problem in number 1, find the problem in number 2. They both came from student labs. And more than one. Okay, Mina's here. Good morning. We'll wait another minute or so, and then we're going to start up, even if I don't have all of you. But I got 10 of you. That's pretty cool. Okay, those who are here, go ahead and start typing. What's the problem with 1? And or what's the problem with number 2? Okay? Aiden is here. Good. I'll leave that there and mark people in as they come. All right, we got any guesses? What's wrong with 1? What's wrong with 2? Ellie says carbonate has a charge of 2-. Ellie is right. And about 6 of you so far didn't know that. Ooh, as soon as I get back to live teaching, you guys get an ion quiz. And you better believe CO3 is going to be on there. CO3 2-. It's really a common ion. Memorize it. Okay? So this is wrong. Okay? So I need, let's see, Ag is 2 plus. No, Aiden, Ag is +1. So you got to memorize that too. Ag is just plus. Alex is here. Good, thank you. Okay, because of that, I got a couple problems here. Let's see if somebody can fix this sucker. Well done, Penelope. So it should be Ag2 CO3. Yeah, exactly. And if it's Ag2 CO3, what's the other problem now with that first one? Thank you very much, Bella. I wish a lot of you had done that on your labs, but a lot of you did not. Ouch. The second one is from somebody's lab too. What's the problem on the second one? What's the problem on number 2? Mg2 plus OH minus forms MgOH2. Looks good to me. Ellie, you're quick. She said it's got to be 2 OH minuses, and it does. It has to be balanced. Okay, last one. And this one's a little long because, yeah, exactly. Good. Thanks, Lola. Got the same thing as did Chelsea and Penelope. Good. Oh, I can't do that. That's a pen. Sorry. Okay, here's number 3, and it goes like this. You guys took CO2 gas and bubbled it into CaOH2, also called lime water. And you got CaCO3, which was the cloudy precipitate. And you got, if you do the math, you'll see you got water left over. Okay. Now, several of you so far have said, oh, that's not right. It's really Ca2 plus CO3 2 minus, although a couple of you had 1 minus there, forms CaCO3. Okay, that is wrong. So no. We need to talk about this. Okay, so why am I getting so upset? Because this net ionic equation is an important one. It's the test for lime water, and it's a test for CO2 if you think about it as well. Okay, now here's the deal. Check this out. CO2 cannot be dropped. It's actively reacting with this. I can't just get rid of it or pretend it's become an ion. It's not an ion, it's a gas. So the gas is reacting with this whole chemical, and I can't drop out water. Water is one of the things forming here, okay? It doesn't just drop out. Even if I say that's aqueous, it doesn't matter. And it's not aqueous anyway. It's a solid that's forming. So you need that whole thing in there for the lime water reaction. Write that down. It's not just the ions, because there is no CO3 2 minus, okay? Not until it forms during the reaction and quickly becomes attached to the calcium ion. Okie dokie? Okay, while you're writing, I hope you're writing, at least the last one. What I'm going to do today, I think, is hunker down and just do notes with you and take your questions as we go through on chapter 1, okay? Where we left off last time, and we're going to really grunt through some stuff this morning. I will take some problem questions tomorrow, Thursday, on stuff, but I want to get through some more of this so you guys have a chance to work through more problems with some confidence of having seen the material ahead of time. Okie dokie, let's dive in. Okay, where we left off last time, I'm going to give you a rough idea, but I'm not going to give the information to you the same way that Cheryl does, because I have my own way of doing it and I like it better. So we're essentially at like 1-3. No, we're at 1-4. Okay, so the way I'm going to give you 1-4 is my way. So we're going to erase that. Hope you got it. If not, I'm going to send you the video anyway. I got 13 of you there. Anyone else who has not said hello yet? I got 12 of you written down, but maybe somebody hasn't said hello yet. So I know who you are and give you credit for being here. Okay, so anybody new? No. Okay, let's talk about, so roughly this is section 1-4, but I'm going to say it's Mr. Weiss's way. It's the same information, but it may not follow her order perfectly. Let's talk about orders of reaction. Orders of reaction. Okay, so in general, the more concentrated the reactants, the faster the reaction. But here's the question we're going to try and answer. But by what factor? And okay, so in general, the more concentrated the reactants, the faster the reaction. But by what factor? That's called the order. And the order, the factor, is pretty simple. It's the number 0, 1, or 2. 0. So the reaction doesn't get affected by the rate of the chemicals at all. 1 or 2. Now, Cheryl may throw you a third order reaction or something, but it's really rare, and you won't get it on the AP test, nor will you get it from me. Okay? So it's basically what we say, it's 0 order, first order, or second order. But here's the thing, it's for each reactant separately. So we're going to look at a couple problems later today and do each reactant separately. It sounds hard, it's not. Once you go through it, my students usually have very good success on this on the AP test. Okay? Okay, I'm going to erase the above part. Think about how I want to best present this to you. Okay, I think I'm going to just talk about each order first. So let's talk about 0 order first, okay? Okay, so if it's 0 order, doubling the concentration of a chemical concentration of a reactant really is what I'm talking about. Reactant does not change the rate. It doesn't mean the reaction stops. It means it keeps going, but it doesn't go any faster, slower. It keeps going at the same rate. And whether I have 1 molar, 2 molar, or 3 molar just doesn't really matter. I don't really understand. Hang with me, Bella. You're going to see what order means, kind of like right now. Okay, so the order is more or less a power. So it looks like this. So for example, the rate would equal some sort of chemical some sort of rate constant, we haven't talked about that yet, times the chemical, let's call it A, to the 0 power. So it ends up being the order, Bella, and everybody ends up being a power. And Errol is here. Thank you, Errol. So I need N Sophie, and I need one other person. Okay, and yeah. Okay, so K is the rate constant. It's a number that is a constant for each reaction separately and depends on temperature. Don't worry, we're going to find these, so that's going to become common use to you as we do a couple of these problems. But what I want you to notice, math people, okay, I got something to the 0 power. What is something to the 0 power? Anything to the 0 power is what? Thank you, Chelsea and Arrow and others. It's 1. So what this becomes is, it's just the rate equals K. Ah. Or I can say, okay. Oh, nice. Good. Whoops. Sorry about that. Yes. Good. I'm going to give you a couple of ideas then about this. Man, where's my eraser? Here it is. So what that means is, if I've got amount of chemical A, then what happens is over time, could be seconds or minutes here, okay, whatever it happens to be, I get less of it. And it doesn't change, it's a constant slope. So if you see this, here's the cool thing. The slope of this line is, of course, that's going down. It's a negative value. So it's not K, it's the opposite of K. But if I can get the slope of this, then I also have what's known as the rate constant. Yeah, I can get it right from a graph. Do you think they're going to ask you to do that? You betcha. Maybe on a multiple choice question, but it's pretty easy. Okay, you can just sort of look at the numbers and calculate the slope of the line, like in math class, and that's the opposite of K. It's a small k, by the way. So that's kind of cool. And here's how to find this. Okay, I'm going to use Cheryl's. She doesn't use A, so I'm going to put hers on here too. She uses C. Okay, so now I'm going to define a couple things. I'm going to use C, okay? Because she uses this and I don't want to cross her, okay? Because you're going to use her value of the equation because it's in the book. Okay, so here's the equation. Rate equation. It's C at time t. In other words, I can get C at any spot on this line if I take the original amount of C, okay, and then I subtract the amount that reacts away. So minus K times the amount of time it goes by, which kind of makes sense if you think about it. So to get the amount here, I got to just take away the amount of stuff that reacts, and I get that by taking the rate times the amount of time that goes by. Yeah, the rate is constant. That is not changing. But what is changing is not the rate, but the amount of chemical. So the rate's not changing. The slope is constant, but the amount of chemical, whether I call it C or A, is going down. I've got less and less and less of it as I make some sort of product. So this is telling you how much do I have left? Well, I got the amount left at some time t by taking the original and then subtracting how much reacts away. This is for a specific rate, not an average rate. Yes, but it's the same for this one, Bella. The rate is constant here because it's got a constant slope. So it's the rate for this particular reaction, and it doesn't change. Not unless the temperature changes, but we'll deal with that later. By the way, I'm going to give you a reference for this, okay? It's way at the end of the chapter, but it's really good. I'm going to give you a page to find all three of these, 0, first, and second order. You ready? So it's page 59. It's a review of these. Cheryl's really good review page, okay? And I'm referring back to that as I talk to you because I don't want to give you the wrong thing. Okay. Could we just use the slope formula? Yine, you can get the slope of this, but then when you do, if they ask for the k, it's the opposite of that. So if my slope was 4, the k would be -4, okay? So it's not, the slope is not equal to k, it's equal to the -1 times k, so to speak. All right, that's if it's 0 order. Good. Let's go to first order. By the way, we're going to do all 3 orders, then we're going to do some examples so you see what the heck how this actually works, okay? So bear with me, all right? Hope you caught up because I got a race here. Okie dokie. Where'd my flipping thing go? My fancy eraser. So let's go to now first order. And again, all I derive with you here, you're going to get on that chart in Cheryl's book, okay? All right, so first order. What it means is if you double the concentration, CONC abbreviated, of a reactant, then the rate of reaction also doubles. So it's 1 to 1, hence first order. Remember first order, if I double the concentration, it does nothing to the rate. No, sorry, that was 0. 0 order, pardon me. If I double a concentration of a reactant, it does not change the rate. First order, if I double the concentration of a reactant, then the rate doubles as well. So it's a 1-to-1 relationship. Or, Achtung, if you triple the concentration, then the rate will triple, okay? Or quadruple and quadruple, you know what I mean? It increases by the same amount. Or triple, etc. Okie dokie. All right, so let's go to Cheryl. All right, what this means is the rate equals some constant, K, and again, it depends, it's different for every reaction, times some chemical, I'll call it A, or you can call it C if you want, like Shirley's, to the first power. Okay? So first order, first power. That's what they mean by order. Now, to get the fancy-dancy reaction, I'm not going to derive it from you. It's got natural log in it. So it looks like this. Here, I'll do it the Cheryl way here. She has K times C. And we'll give you the Cheryl version. The natural log ln of C at time t equals negative kt, so k times t, plus the natural log of the original concentration of reactant C. Okay, now I'm going to give you the other version that I like better, because that's me. Or, and this is the one I use in class quite often, the natural log of this fraction, C at time t over C original equals negative k times t. Are they the same? Yeah. Somehow I find this easier to look at and easier for me to memorize. Are they going to give you these in some form on the given information sheet? Yes. And we'll look at what they give us this year later on. But the first order one's so important. I would memorize this sucker, either this one or this one. I'll just write no. No one or the other of them, okay? All right, let me take your questions here. Okay. Okay, the variable under the first C, Aiden, is T, and it means the concentration of chemical C at time T. And over here, I got the concentration of chemical C original, the original amount that I had. You're welcome. Huge. Okay, the other thing you need to know is how to get, if I graph this thing, how do I get a straight line? So for first order, it's time again down here, I think. I better take a look. Yeah, it's time. Could be in seconds, could be minutes, or if it's like nuclear decay, could be years. Okay, and on this side, it's natural log of C. And it goes down. And it turns out the slope of this thing, if I do this, is just like the zero order graph, although the axes were different. The slope gives you negative k once again. Pretty good deal, huh? Okay, now, folks, I think you had this, some of you from me in ninth grade physics, but if not, you probably had it with somebody. Remember when we talked about half-life of radioactive elements? Okay, like uranium has a half-life, or plutonium has a half-life, carbon-14 has a half-life. All those radioactive element problems, they're all first order. So that's a good thing to know, because if they give you one on the AP, you know it's first order already, okay? So all radioactive elements decay, not like a log, but radioactive decay, in first order reactions. Ta-da! So good thing to know, right? We're 2/3 of the way there. So let me pause for you to finish writing, and then we're going to do second order, and then we're going to get to business and try some of these suckers, okay? We're doing just fine. Any questions before I erase this stuff? Good. First order is really common on the AP. So that one I want to make sure we got down good. And that's everything I need you to know about it. Again, this is on the page 459 review chart that Cheryl has. That's a good chart. Okay? Yo, away it goes. If you didn't get it, I'll send this video to you later. Let's go and do second order. So for this one, you can kind of guess if we double the concentration of a reactant, the reaction rate increases by times. Oh, fill in the blank. Let's see if you're awake this morning. Yes, Aiden, it is, regardless of C. It'll vary with each one, but woo, some of you are quick. Alex and Chelsea got it right away. So it is indeed 4 times. We'll see why that is mathematically as well. Yeah, good. Well, got it too, as did Anthony. Good. I can also say, or if we triple a concentration, the reaction rate does what? Can you guess? So if we triple it, if we double it, it increases by 4. If we triple it, it increases by See if another one or two figured out. Exactly. Good. Lola, Aiden, Chelsea. Increases by 9 times. Why? Well, it makes sense if you think about it. So here's what we mean. We would say the rate is equal to K times some chemical. I'll do C because I'm tired of worrying about what Cheryl has, to the second power. So see, if we like double it, then it'll be 2 squared, which would be 4. All right. If I triple it, 3c squared would give me 9 because I gotta square the 3 too. I think a lot of you realize. Yeah, so that's kind of how this one works, okay? Ute. Let's get the nuts and bolts out of it. The equation, again, I'm just going to give you, called the integrated rate equation. Anyway, the equation to get numbers is 1 over C at time t equals K times T, so KT, no minus this time, plus 1 over C original. And if you think about it, that's going to give you a graph too that's going to be linear. If I got 1 over C, and this time because it's 1 over that, it's going to be linear going up. And here I got time down here still. The slope this time is actually K because it's a positive raising line. So for 0 in first order, the slope is negative K. For second order, the slope is K. I know you're graphing different things for each one, but that's just something to kind of put away. Again, all on page 59, okay? A wonderful review page for you. And again, second order, Cheryl's got nth order and so on. God, you don't need all that crap. You really don't. So I'm not going to worry about third or fourth order. That's really so rare. The most common is 0, first or second. And the most common of those, I think, is first order. Okay, you ready to play the game? The game's actually kind of fun now that you got the rules. And the game is easier. I gave you now all the hard stuff, okay? So let's learn how to use it and have some fun. Okay, first thing I got to do is erase the frickin' board again. We okay? I think we're okay. I'll let you do some of these online. It involves lots and lots of data. So unfortunately, we got to write some data here today. Okay, first thing we did, so I'm going to say example, and I need a reaction on my old notes. Where is that sucker? It's CH3CHO. Plus, no, it's a decomposition. So it breaks down to CH4 methane gas plus CO2. No, CO. All gases. So find the reaction order. For this rate. For rate equals K times. All right, we only got one reactant, don't we? So we're going to write the chemical in brackets. CH3, CHO. And we're going to write M up here. We don't know what it is. So we're going to let our variable be M. So essentially, we're trying to find the reaction order M for this thing. How do we do it? We do it with lots of data. Okay, you ready? Here we go. We got to make a chart of data. We're going to have 1, 2, 3, 4 experiments. So, so here's the concentration of the chemical. Here, let's write it over here. So, experiment 1. Experiment 2. Experiment 3. Sorry about my funny E's. And experiment 4. Experiment 1, 2, 3, 4. So for each one, let's give you a concentration of CH3, CHO, and we're going to give you then also a rate. We talked about the rates the other day. This one's going to be in moles per liter second. Moles per liter per second. So the seconds are down in the basement as well, okay? So how many, essentially it makes sense, doesn't it? How many moles per liter are changing every second? So moles per liter second. All right, here we go. So we got 0.1 molar. We got 0.2 we got 0.3 molar, and I got 0.4 molar. And here's the rates. I'm not going to write a label because I got the label here. And actually, I don't have to write the label here. I did it to be nice. It's all moles per liter, but that's what the brackets mean, moles per liter anyway. Okay, so let's get some rates. I'm going to do those in another color so I can see them easier. Maybe you can too. So this is 0.085. This is 0.34. This is 0.16. And this is 1.4. Okay, strategy. Okay, choose 2 experiments. And compare. Compare concentration and rate. I'm going to try and write kind of small so I can keep this numbers on here for you. So sorry, I can read it if you can't see it, but I hope you'll be able to see it. So let's stay with blue a little bit. Okay, I don't know any better, so I'm just going to go and compare 1 and 2. Okay, experiment 1 with experiment 2. But you could use really any of them mathematically. Okay? Okay, so the rate of 1 divided by the rate of 2. Oh, nope, sorry. Let's make it 2/1. Pardon me. Why? Because 2 is bigger. Put the bigger one on top. Sorry about that. Is 0.34 divided by 0.085. And those are both in moles per liter. Let's do it a smart way, okay? So moles per liter, capital M, seconds minus 1. Can we do that? Moles per liter, seconds minus 1. That means it's in the basement, right? The little s minus 1. Okay, so divide that out on your calculators, could you? 0.34 divided by 0.085. God, that looks awful. Okay, see what you get. And then next to it, those without a calculator can do this. Let's take the concentration of CH3, CHO in experiment 2 and divide it by the concentration of CH3, CHO in experiment 1. Well, that's easy, isn't it? It's what? It's 0.20 molar divided by 0.10 molar. And that gives you, yay, good. Thanks, everybody. So this gives you 4. Yeah, I'm going to put a little block here. And this one gives you 2, doesn't it? You might say, ooh, that's kind of weird. But I'm going to show you how to do it now. Okay, now I can erase because we got the data we need from our data up above. Here we go. Okay, so we're not done yet, but we've done really the hard part. All right, so the rate equals K times the concentration of CH3, CHO to the M power. Well, the rate increased by 4, so I'm going to put 4.0 equals K times, and this I increased by 2, didn't I? And I think you can see already, can't you? To make this work, M has got to be what power? So M is what? We're not worried about K yet. Don't worry about K. So what power has M got to be to make this thing 4? Thank you, Lola and Aiden and others. Great. So it's 2. All right. So this is second order. Well, the only chemical we got, CH3, CHO. Another way to say it is I can now put a 2 up in there. So the rate equals K times CH3, CHO to the second power. It's a second order reaction. That's what you've discovered using the data. Now, I've been ignoring this K. You might say, well, what's the deal, Mr. Weiss? What's this K thing? Well, let's find K. What the hey? So I'll say now, get K. Psst, it's easy. Use any experiment, 1, 2, 3, or 4. Use the data. So I'm lazy, so I'm going to use experiment 1. So here we go. The rate was, so experiment 1. So the rate was 0.085 moles per liter times seconds to -1 equals K times 0.1 molar, 0.10 molar to the second power. Okay, don't forget that. We went to all that trouble to find the power, remember? All right, so let's get K. When the numbers always come out so easy. Yes, isn't that nice, Aiden? The answer is yes, the numbers will come out always easy. In fact, sometimes it's so easy you can just do it mentally. And I'm going to invite you to do that to save time, okay? So you can use this method that I just showed you, the mathematical method, to find the order. It always works. Or you can use the mental method, and I'll teach you that too to save time, okay? So yeah, it comes out nice. Okay, somebody got a number for me? Could you plug that in, please? So solve for K, divided by 0.10 squared. And somebody else got to figure out the label for me. Sometimes on the AP, you get a point just for the correct label on the K. Okay, give you a hint. We got to go ding, ding, divide by the label as well. And then that sucker's still going to be there. Okay, somebody got a number? Lola does. I'm going to write it and then others can verify it. So we got, I got 2 different numbers from 2 different people. I got 0.075, I got 0.0085. I'm going to go with 0.0085. So we're dividing by 0.1 and 0.1. So 0.0, could some others punch that out? I'm not sure either of those are correct. 0.085 divided by, 0.01. No, we got to divide, so it's going to be, yeah, good. It might have, thank you, okay. Aiden's got it, Lycia's got it, Chelsea's got it. So if I divide by 100th, then I'm going to get 8.5. Somebody else, you got the label for me? Thank you. Good. Thank you, everybody, for doing that. Yeah. So so I'm dividing by 0.1 squared, Amina. So 0.085 divided by 0.1 equals, and then divided by 0.1 again equals, and it's going to be 8.5. So punch it out a couple more times. Okay, so what happens here? This is squared, so is the label. So one of these suckers goes, but I got to divide by it. So it's sort of like the moles per liter is down here, the one that's left over. You know what I'm saying? Because I got to divide by moles per liter squared. And the seconds is down there as well. Now, that looks ugly. So what they do in the AP world is they say it'd be 8.5 moles per liter to the -1 times seconds to the -1. That means they're both down in the basement, okay? So that, my friends, is the K. So I could rewrite this again and say the rate is 8.5 meters negative, moles per liter -1 S -1 times blah, blah, blah to the second. You know what I'm saying? Maybe I should do that. Okay, I'll move up here. So, final answer. If I want the complete rate law, is rate equals 8.5 moles per liter to the -1 seconds -1 times concentration of CH3 CHO to the second power. Voila. Voila. Whew. Okay. Good. Okay. Your turn. I'm going to give you some to work on for tomorrow, okay? Because I don't know if we'll get the whole thing done because we're getting towards 11 and I have to set something up before my next live stream. So, here's a data from an old friend of mine that I taught with for many years. And let's have you try it. All right, given I got 2 ClO2 gas plus F2 gas forms 2 ClO2F. Also, surprise, a gas. And here's the data. We're going to have experiment 1, 2, 3. And let's give you some concentrations of ClO2. I'm doing them in moles per liter, but they're gases. They probably ought to be in atmospheres, but don't worry about it for now, okay? Because that's what my old friend gave me too. He gave me moles per liter. And then the rate. And the rate is in moles per liter times seconds to the -1. So moles per liter seconds. Okay, sorry I moved that too far up, but anyway, okay, you get it. Okay, so these are concentrations, so we're going to have all these in moles per liter, so I'm going to say 0.010, 0.010, 0.020. And here, this one, I got 0.10, 0.40, and 0.20. Now the rates are 2.4 times 10 to the negative third. The next one, 9.6 times 10 to the negative third. And the third one, 9.6 times 10 to the negative third. Hey, now it's more exciting because what? I got 2 reactants instead of 1. Does it make it twice as hard? Not really. Okay, we got 4 minutes. Let's talk about it, and then I'm going to have you do the math. So I'm going to say, on top of all your other work for AP Chem, which is doing problems in the chapter, I'm going to say finish for tomorrow, or I'll just say due for Thursday. It'll probably just take you a few minutes after this hour to finish up. You can take 5 or 10 minutes and probably done with it. Use the method I gave you already, and then I'll show you maybe a different method tomorrow to do it mentally. But we can kind of see what's happening. You want to do the reactants one at a time, okay? So for now, you see how this one's the same for ClO2? So let's just do this one here. You want where it's changing. No, Bill, I don't want it turned in. I just want you to have it done for so we can talk about it at the beginning of class. But no, I don't have a good spot to turn in at this point. Okay, you want 2 experiments where only one is changing. So let's take experiment 1 and 2. Why? Because this one's the same, so I can concentrate on this. Okay, this is increasing how many times, gang? 4, right? Okay, you can see that. So you got to figure out how many times the rate is changing at the same time, all right? Mentally, you could just about do that right now. Okay, then you got to check out the other one. So for the other one, ideally, you would have one where F2 doesn't change at all, but you don't have that. So instead, you got one where F2 is going from 0.1 to 0.2, and you can figure out from your previous work. Oh, Feeney's here. No, don't submit it. They already asked that. No, don't turn it in. Just do it. Okay. So from here to here, it's doubling, but you'll know what that should do to the number. And instead, I get 9.6. So you can see if this one also doubles, you're going to use a little logic and try and figure out what the effect of doubling this one is. But here's my suggestion. Do F2 first. With experiment 1 and 2. Okay? Then I think you'll see with your logic how you can figure out the other one with 1 and 3. How you can figure out the concentration of ClO2 and what order that. So you can have 2 different orders. So find the order for each chemical. That's what you're going to find. Find order for F2, then ClO2. Okay? Now, this is a little harder, but you're AP students. It's really not that much harder. So use some logic, okay? You guys are smart cookies. You should be able to figure it out. Okay, I got to write down that I got Feeney here as well. So the only one I don't have is Anne-Sophie, and I think she can't make it. Am I right? Anne-Sophie, you're not out there. Everybody else I think I got. And thank you. I hope to see you tomorrow. Same spot, my basement, different time, and I'll send that information to you. And once we do this one and maybe one other one, then we'll take some time for your questions tomorrow. Okay? All right. We're out of time. So I'm going to wish you well, unless you've got any last questions. So give that a try over the next few minutes. See if you can do it. And we'll see you tomorrow. You're welcome.